Hey everybody, welcome back to astronomy. I'm up in my lab today, and the reason for being up in my lab is I wanted to demonstrate stuff with globes and models of the moon and stuff. And I've got this really nice video camera, and I've got the lights off, but the video camera is so nice that it adjusts for the brightness of the room, and so you can't even tell the lights are off. Hopefully when I've got some lit things in the room, you'll be able to tell. So I'm going to be moving the camera around a lot today. I'll probably not always be looking to the camera because the camera's over here, but my laptop's over here. I'll try to remember to look at where the camera is. I want to talk a little bit today about the Earth-Moon system, really quickly. This is an accelerated class, so some things had to give in order to fit it all into 10 weeks. One of the things that I've decided should give is just talking about the Earth and what it's like on the Earth and what you see when you look up in the sky and what causes the seasons and all that stuff. You guys should know what causes the seasons and the phases of the moon from middle school Earth science. So I don't feel like I should have to spend loads and loads of time on that. The Earth spins on its axis, but its axis is tilted relative to its orbit around the sun. So I need to get a little bit further away from the camera if I can. Maybe point the camera down a little bit. So there's the Earth. I'm going to move my sun. My sun is an old-timey, overhead projector. Okay? One of these jobbies. So that's over here. That's playing the role of my sun. So let me move my sun so that it lights half of my Earth. You guys can see that nicely from where you are. That. Okay. So you can see right now that this half of the Earth you can't see because it's dark. This half of the Earth you can see because it's light. The sun is over there. The sun spins on its axis this way. So there's the US. So here's sunrise in Virginia. Virginia goes around to the other side of the Earth. Here's sunrise in, I can't tell what's what on the map because the camera's got my picture reversed. Sunrise in Australia and China, and sunrise in India, as the Earth spins around on its axis this way. So the night side of the Earth is dark, the bright side of the Earth is in sun. At this point in the Earth's orbit, right now, the way I have this globe set up, notice the axis is tilted towards the sun. So right now it would be summer for the northern hemisphere. If you're in the northern hemisphere, the sun would be higher in the sky because you're tilted towards it. If you're in the southern hemisphere, the sun would be lower in the sky because you're tilted away from it. 6 months later, when the Earth goes around to the other side of the sun, it will be tilted away from the sun. So now it is winter. Where's the United States? It's winter in the United States because we're tilted away from the sun. When we look at the sun, it is low in our sky. And if we're in South America, if we're in South Africa, or if we're in Australia, the sun is high in the sky because we're tilted towards the sun, and we would have to look up high in the sky to see the sun. So the seasons are caused by the fact that the Earth's axis is not vertical relative to its plane of orientation. Sometimes we're tilted away from the sun, sometimes we're tilted towards the sun. The direction that the Earth's axis points stays the same over the course of a year. So as the Earth goes around the sun, it goes around with its axis always pointing at Polaris. It's just an accident that there happens to be a star there called Polaris. But that tilt is responsible for the change of the seasons. When the sun is high in the sky, it hits the Earth directly. Its sun's rays are more concentrated. When the sun is low in the sky, its sun's rays are more spread out. I think that's all I'm going to say about that. The moon orbits around the sun. This moon it's a little too big, but it's close. I tried to find a moon that is almost the right size for the Earth. It's actually not too bad. Okay, if this is my standard classroom globe to stand in for the Earth, the moon's about the size of a softball. It's quite a bit bigger than a softball, but to scale, that's not too bad. The moon is very big in our solar system. The moon is very large compared to the Earth for most moons. Right? Mars's moons are tiny little asteroids the size of Petersburg. Jupiter's got moons bigger than our moon, but it's hundreds of times bigger than the Earth. The only other planet and moon that are as close in size are Pluto and its big moon Charon. but we don't even consider Pluto a planet anymore. So we'll talk about that. But our moon goes around the Earth in an orbit, and as it goes around the Earth in its orbit, it is lit at different angles by the sun. So if you were the Earth, you meaning you there where the camera is, and the moon was here, you would see a slightly bigger than full moon. When the moon goes around to a different place in its orbit, you would see it lit at a different angle. When the moon is a little towards the sun, like so, you would see a crescent moon. You can see that when the moon is sort of in the direction of the sun, you don't see it fully lit. You only see it partially lit. And as it comes around to this side, you would see it half lit. And then as it comes around over here, you would see more and more of the lit side until finally you would see a full moon. And then as it goes around here, you would see it half lit again. Then when it comes around the backside, you would see a crescent again. So the direction of the Earth, moon, sun determines the phase of the moon as the moon goes around in its orbit. When it's towards the sun, we tend to see it crescent. When it's the 90-degree angle, we see half. When it's on the other side of the Earth, we see it full. And when it's directly between the Earth and the sun, we don't see it at all, except on rare occasions when the moon passes directly between the Earth and the sun, and that's called a solar eclipse. You might imagine that if the moon goes around the sun, it should pass between the Earth and the sun every month. Well, it does, but it doesn't pass directly between the Earth and the sun because the moon's orbit is tilted a little bit. It doesn't orbit exactly in the plane of the Earth's orbit. It orbits at a slight angle. So sometimes it's a little below the sun, sometimes it's a little above the sun. Okay. It would be easier to illustrate that if I pointed the camera at the sun. I'm not sure how. I apologize if the sound is like fluctuating like crazy. There's the sun. There's the moon. Okay. The moon goes around the Earth. There it goes. It goes around the Earth. Because its orbit is tilted, though, sometimes when it's in this direction, it's a little bit above the sun, and we just can't see it. Sometimes as it's in this direction, it's a little bit below the sun, and it can't see it. This tilt of the moon's orbit is about 5 degrees. But every once in a while, as the moon comes around in its orbit between the Earth and the sun, it will pass directly in between the sun and the Earth, and it will block out the sun, and that is called a total solar eclipse. There was a total solar eclipse visible not too far from here in 2017. It was a partial solar eclipse from here in Virginia. The moon covered up about 85% of the sun. I actually drove down to South Carolina to see where it was total. And one of the words, you can see where the sun was completely blocked out by the moon. It's well worth the drive. If you can, in a day, drive to a place where there is a total solar eclipse, it is 100% worth it. The next one is in the late 2020s or early 2030s. It cuts down from kind of New England all the way down to Texas. I think from here you'd have to drive to maybe Pennsylvania or maybe to Western Tennessee in order to see it. I don't know the exact path. I'll find a link and I'll post it up to Canvas if I remember. Once in a lifetime experience, well worth it. If I get a chance, I'll also post the pictures that I personally took of the 2017 solar eclipse. I'll post them up to Canvas as well. If you were off the Earth, if you were out in space and you were looking at the Earth when a total solar eclipse happened, what you would see is the moon's shadow pass over the Earth. This moon is too big to show this. Let me get a smaller moon. Hold on a second. Let me move my camera a little bit. So here you are out in space. There's the Earth. I'm holding this tennis ball. This tennis ball is the moon. If you were out in space watching a total solar eclipse happen on the Earth, what you would see is the moon's shadow pass over the Earth and trace a path. That didn't do a very good job. Okay, the moon shadow there, that's a little bit better. The moon shadow pass over the Earth and darken a strip of the Earth. And if you were at that point on the Earth where the moon shadow is falling, what you would be seeing is the moon blotting out the sun. Okay, so a total solar eclipse happens when the moon gets between the Earth and the sun. It doesn't happen every month because the moon's orbit is tilted a little bit. Sometimes it's a little too high, Sometimes it's a little too low. There's only a solar eclipse when the moon just crosses the Earth's orbit at just the time it's between the Earth and the sun. That's why it's relatively rare. Now, the flip side of a total solar eclipse happens when the Earth, moon, and the sun are in a straight line this way. When they're in a straight line this way, there's something called a total lunar eclipse. A lunar eclipse happens when the moon passes through the Earth's shadow. So here's the Earth, the sun's over there, the Earth is making a shadow in space as the moon comes, it's my shadow, not the moon shadow. Let me stand on the other side of the moon. As the moon comes around in its orbit and passes through the Earth's shadow, the moon appears to get darker. If you are on the night side of the Earth, when the moon goes through the Earth's shadow, what you see is a dark shadow gradually cover the moon, turning it black or sometimes a reddish brown color. The red color comes from the fact that some of the light that's just making it to the moon is coming through the edges of the Earth's atmosphere. And you know, when you look at the sun through the edges of the Earth's atmosphere, like at sunrise and sunset, that light becomes reddened because the Earth's atmosphere scatters the blue light. Right? So when the moon passes through the Earth's shadow, a little bit of light around the edges of the Earth gets to it, and that light is sunrise and sunset light, which has a reddish color, and then the moon comes back out again. Lunar eclipses are more common than solar eclipses because the Earth just casts a bigger shadow in space than the moon casts. So it's much more likely for the moon to pass through the Earth's shadow than it is for the Earth to pass through the moon's shadow because the Earth's got a bigger shadow. So there's a lunar eclipse every, 18 months or so. There's one every year and a half or so. Lunar eclipses are not that rare. They're also not as spectacular. The moon just gets kind of dark. If you're not really paying attention to the moon, you probably wouldn't notice it was happening. Those are eclipses. That's all I'm going to say about it. I'll post a crash course video about eclipses or a PBS video about eclipses if you want. If you hadn't heard that before and it's all brand new to you and it's hard to follow, watch the internet video and that will help. But I'm not here to talk about what happens on the Earth. I'm here to talk about what happens when we get far away from the Earth. So that's just a really quick review of just this aspect of looking at the moon that happens every once in a while. I do want to talk, though, about a thing that happens between the Earth and the moon that is going to be important, not just for talking about the Earth and moon, but talking about the solar system in general, and that is the phenomenon of tides. Okay. The moon sits in space, orbiting around the Earth. So I can get both the moon and the Earth in my frame here. Moon, Earth, that'll do it. And the Earth exerts a gravitational pull on the moon. That gravitational pull is what holds the moon in its orbit around the Earth. That was discovered by Isaac Newton. We know that gravity is responsible for holding things in their orbit. But the moon also exerts a gravitational pull on the Earth. When we think about planets orbiting or moons orbiting a planet, we think about the planet sitting still and the moon going around it. That's actually not what happens. What happens is the Earth and moon orbit their center of mass. Now, the Earth is much more massive than the moon. So the center of mass of the Earth-Moon system is close to the Earth. Basically, the Earth and moon orbit around the place where if you put the Earth and moon on a seesaw, it's the place that seesaw would balance, which is actually inside the surface of the Earth, because the Earth weighs so much more than the moon. But as the moon goes around the Earth actually goes around in a little circle. The technical name for that point is the Barry center, Bary, the center of mass of the Earth-Moon system. Or if you want to think about it, if you made a mobile of the Earth and the moon, the place where you'd have to tie that string so the mobile didn't tilt, that's the place that the Earth and moon orbit around. Obviously, this is not to scale here. To scale, if I was going to put the Earth and moon to scale, it would look something more like this. The Earth would be here. You can't see that, I'm too far away. And the moon would be way over here. So as the moon orbits around the Earth in this great big circle of the moon's orbit, that is 220,000 miles or whatever in diameter, the Earth moves in a tiny, tiny little circle that's totally enclosed inside the Earth. That's one thing to keep in mind about the Earth's motion. The other thing to keep in mind about the moon's gravitational pull on the Earth is it's not the same everywhere. If I take my moon here and my Earth here, and again, I'm going to exaggerate the distance between the Earth and the moon just for the purpose of illustration. If you are on this side of the Earth, you are closer to the moon than if you are on, I have to get both sides of the Earth in, this side of the Earth, right? This side of the Earth over here is further from the moon than this side of the Earth. That means the moon's gravity pulls harder on the close side than it does on the near side. That greater force on this side than on this side has the effect of like pulling the Earth this way, like a piece of taffy or a piece of clay. And the fact that one side is being pulled stronger than the other side tends to elongate the Earth. That force is called a tidal force. A tidal force is a force due to the difference in the strength of gravitational pull between one side and the other. There's a tidal force of the Earth on the moon. There's a tidal force of the moon on the Earth. There's a tidal force of the sun on the Earth. Now, the Earth is mostly solid, so that tidal force doesn't stretch the Earth into a non-circular shape, but it does stretch the Earth's water into a non-circular shape. So what this tidal force does, because this side of the Earth is closer to the moon, you can't see the moon anymore because we're too close. Because this side of the Earth is closer to the moon, the water is pulled more towards the moon on this side. And on the other side, the Earth is pulled more towards the moon than the water. So the water has the kind of shape of an ellipsoid, an oval shape. So as the Earth spins around, it goes through a place where the water is high, then a place where the water is low, then a place where the water is high, then a place where the water is low again. So twice a day, we go through a high tide, a low tide. Remember, the moon is over here. It's really hard to get all these things on screen. Okay, so right now it is high tide in Australia. It is high tide in off the coast of Africa. It is low tide here in Indonesia, and it is low tide here in Mexico. Now it is high tide in Mexico, low tide off the coast of Africa, low tide in Spain and in the Mediterranean, high tide over here in Australia and Indonesia, and low tide over here, wherever's over here, say California. So twice a day as you go around the Earth, the moon goes from being on your side to 90 degrees to the far side to 90 degrees to your side again, and that's high tide, low tide, high tide, low tide. So 2 high tides, 2 low tides every day. That elongating force also pulls on the Earth's crust. There are actually tides in the ground. The ground raises by a centimeter or 2 on one side of the Earth compared to the other side of the Earth. The actual dirt, okay, moves up by a half an inch, because when you're on the side of the moon, you're being pulled away from the center of the Earth a little bit harder than you are when you're 90 degrees around the circle. This tidal force would have been more important when the Earth was molten, when the Earth wasn't completely solid inside. It would have elongated the Earth more. There are also tidal forces of the Earth on the moon, and these forces were also more important when the moon was very young. I'm not sure. Again, I'm fighting against the camera's attempts to make everything look well lit. This is the near side of the moon. Remember, I said that when the moon goes around the Earth, the same side always faces us, right? That doesn't mean the moon doesn't spin. It means the moon spins once every time it goes around us, so that one side of it is always facing the Earth. And I call that tidal locking. Why is that called tidal locking? Because that force that slowed down the moon's rotation until one side always faced the Earth was caused by the tidal force between the Earth and the moon when the moon was still young and molten, and the Earth could actually change the shape of the moon a little bit. One of the side effects of that is if you look at the moon's surface, the side of the moon that faces the Earth has more of these flat regions called seas When you look at the moon through a small telescope, they look like flat gray regions with no craters. What caused these seas was that in the distant past, impacts from comets, asteroids, meteors kind of broke through the moon's surface, and then lava flowed up through those craters and filled them up with a flat new land. And that flat new land has fewer craters on it than the old land, the old parts of the moon. My camera's making a shadow on my moon. So these flat regions on our side of the moon, these seas, and they were called seas because back in the 1600s, some people thought they were full of water. They're not full of water, they're full of solidified lava. But these flat regions on the moon with no craters are young moon because lava flowed out of these impact craters and filled up these basins. If you look at the far side of the moon, there are almost none of these. The far side of the moon is all cratery compared to the near side of the moon. Why is that? It's because the crust of the moon is actually thinner on the Earth side than it is on the other side. And that is, again, due to these tidal forces, the fact that the moon's being pulled on one side towards the Earth harder, and that actually made the crust thinner on the Earth side because the core is being pulled towards the Earth and being pulled away from the far side of the moon. So the difference in the moon's appearance from the far side to the near side is actually due to the tidal forces between the Earth and the moon. I feel like I should draw a diagram showing how tidal forces slowed down the moon's rotation. And then after I do that, I'll stop. Let me turn the lights on. Let me go to the board. My whole setup here is portable today. Let's see if I can draw a diagram that illustrates that tidal slowing down. Come on. So I try to remember not to keep talking when I walk away from the camera. Let's see, I need a black pen and a blue pen. And I need to get way closer to the board so you guys can see it. Maybe like that. Here is the Earth. And we're not focused on the board. Come on, focus on my hand and now focus on the board. There we go. Okay, now we're focused on the board. Here is the Earth. I'm going to draw, again, slightly exaggerated, the effect of the tidal interaction between the moon, so here's the moon, and the Earth. Come on, stop trying to focus on me, focus on the screen. There we go. Maybe if I get far away from the camera. This side of the Earth is pulled stronger towards the moon, so the water kind of bunches up on this side. This is, again, a bit of an exaggeration, but I have to exaggerate it in order for you to see it. This side of the Earth is being pulled stronger to the moon than the water, so the water bunches up on that side. So these tidal bulges in the Earth's ocean are a result of the different, stronger force of gravity pulling the Earth that way, okay? But the Earth isn't just sitting still, the Earth is spinning. As the Earth spins on its axis, this tidal bulge is dragged around by the Earth's rotation. So the real picture looks something like this. And again, I'm going to exaggerate it a little bit because if I don't exaggerate, you won't be able to see what's going on. I've lost all my erasers. If we draw a line from the Earth to the moon, this tidal bulge of the oceans is actually not exactly lined up with the moon. It's a little bit off. And the reason it's a little bit off is because the Earth's rotation pulls the oceans around with it. Imagine we're looking down on the Earth from the North Pole, so we're above the North Pole looking down. Because this bulge is a little bit off, this bulge exerts a gravitational pull on the moon that is off center. It also exerts a frictional force on the Earth. I'm reading that too small, aren't I? It exerts a frictional force on the Earth that slows down the Earth's rotation. So this off-center tidal bulge over the past several billion years has had two effects. One is it's slowing down the rotation of the Earth and the moon on their axes. The effect of that is that the moon's rotation is now so slow that it's synced up with its orbit. The Earth's tidal bulge has pulled on the moon to the point that its rotation has slowed down to be a month long. The moon is also slowing down the Earth's rotation. The Earth's rotation is getting a little bit slower every year. If you go back to the time when there was nothing living on the land and all the life was in the seas, 2.5 billion years ago, let's say. A day on the Earth was about 18 hours, not 24 hours. In those 2 billion years, the Earth's rotation has slowed down from 18 hours to 20 hours to 22 hours to 24 hours, and it's still slowing. The other thing that's happening, you might say, well, where's that energy going? If the Earth's rotation is slowing down and the moon's rotation is slowing down, isn't there some law of physics called the law of conservation of energy? Doesn't that energy have to be going somewhere? Yeah, it does. Where's it going? It's making the moon orbit faster. So the moon is actually slowly spiraling away from the Earth. So over the past 2 billion years, the Earth and moon's rotation have been slowing down, and that energy has been boosting the moon into a higher and higher and higher orbit. So the moon is moving away from the Earth. If the Earth and moon hang around long enough, the Earth and the moon will be tidally locked together to the point where the Earth's rotation and the moon's orbit are synchronized. So you would only be able to see the moon from one point on the Earth, and it would always be in the same place. Now that will never really happen because our sun will burn out and toast the Earth and moon before that has the chance to happen. But if there was an infinite amount of time for this interaction between the Earth and the moon to convert the rotational energy into orbital energy, that's what eventually would happen. The Earth and moon will be exactly tidally locked to one another. Okay, a day and a month will be the same length, and you'll only be able to see the moon from one place on the Earth. Again, the sun will kill us all before that happens, so it's not really going to happen, but that's what the end point of this process will be. What's the important takeaway about this? One, it's just cool to know that the moon is slowing down or the moon's orbit is speeding up and the Earth is slowing down and the day gets a little bit longer every year. That's just a fun fact. But this notion of a tidal interaction between a planet and a moon that has the effect of exerting a stretching force on the Earth's ocean or on the moon's rocks that causes the crust to be thinner on one side than the other is true of any planet-moon system, and it's true of any planet-star system. By the way, this process of the Earth exerting a tidal force on the moon and slowing it down is the same thing that the sun is doing to Mercury, that slowed down Mercury's rotation to this weird 3-to-2 ratio of its spin to its orbit. So tidal forces are important. They're important for the Earth as a planet because we've got a moon that's so big, but they're important for all moons, especially if they're orbiting a big planet. So in a couple of weeks when we talk about, well, we're probably going to talk about Jupiter and Saturn this week, but we're going to talk about their moons maybe the week after next. The tidal force that Jupiter exerts on its moons or Saturn exerts on its moons could be a very important driver of the energy of the rocks in the interior and the structure of that moon. Okay, why don't I leave it there. I know that was kind of a quick and scattered, and hopefully the sound isn't all crazy from me moving around so much. Probably a really good lecture to read the book chapters, and I'll make sure I select the book chapters and post them to the pages section of Canvas. And a good one, again, if you're really not 100% clear on the eclipse business, why there isn't a solar eclipse every month, what's the difference between a solar eclipse and a lunar eclipse, some nice animations from the video should help clear that up. All right, so I'm gonna go ahead and stop that there. Boy, I hope I remembered to hit record. Let's see. I did. All right, I'll see all you guys in the next video.